The last heuristic I want to cover is that of representativeness. Let me explain this using a scenario. Say that we surveyed all the families that have exactly 6 children in a given city. Say that we also found out that there were 72 families for whom the exact order of births of boys and girls happened to be the one shown here. So girl, boy, boy, girl. Let me ask you the following. What is your estimate of how many families that were surveyed would have this other order? Boy, girl, boy, 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 boy. And to make this easy, let me just boil down, let me just give you sort of 3 broad alternatives. Do you think it's going to be more than 72? Exactly 72? Less than 72? Which one would you pick? As usual, pause if you don't want to hear this. As it turns out, most people tend to pick less than 72. See, in other words, most people have an intuition that the second sequence, the BG, B, 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 is less likely to occur than the first sequence. Right? And they think it's less likely because they think there are fewer than 72 families. So there are fewer families that would have the second sequence than the first. Hence, it must be that people think that the second sequence is more rare than is the first sequence. Yet, according to probability theory, the 2 sequences are actually equiprobable. They have exactly the same likelihood of occurring. If we assume that the probability of sex at birth, of a certain sex at birth of a child, is independent of the sex of the other children in that given family, then at every birth, the probability of having a B is 50%, and the probability of having a G is 50%. So what is the probability of this particular sequence here? Well, 50% times 50% times 50% times 50% times 50% times 50%. So that's 1/2 to the 6th, or just about 1.5%. What is, according to probability theory, the likeliness of the second sequence? Well, 50% times 50% times 50% times 50% times 50% times 50%. That is to say, 1/2 to the 6th. Again, 1.5%. Any specific sequence of 6 births will have the exact same likeliness of occurring. And yet, it is undeniable that the first sequence, GB, GB, BG, feels subjectively way more likely to occur than the second sequence, BG, BB, BB. It's just an intuition that we seem to have. The question, of course, is why would that be the case? Well, one answer is the representativeness heuristic. And this says that when we have to judge how likely a certain event is to occur, rather than using probability theory to try to decide how likely it is, we use other factors. We use a heuristic, a strategy that is based on other factors. Specifically, it's based on 2 main things. First, how representative is the event of the population from which it is drawn? Second, the degree to which the event reflects the salient characteristics of whatever process has generated it. In our case, randomness. Let me make this more concrete. According to the representativeness heuristic, we find the first sequence, GBGBBG, to be more likely to occur than the second one because first, the first sequence is just more reflective of the actual distribution of G's and B's in the population, which is, vaguely equal. So it makes sense that we're very likely to get a sequence within which the G's and the B's are vaguely equal. Second, the first sequence is also just more consistent, more representative of what a random sequence should look like. A random sequence feels like it should have, almost even numbers of the possible outcomes. So the first sequence, GB, GB, BG, kind of has that expectation into it. The second sequence, B, G, B, 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 it feels like, you shouldn't get something like this just by chance. It almost feels like there's something else going on that is causing every birth to be a B, instead of having a mixture of Bs and Gs. And you can replicate this with coin tosses. If you imagine the Gs and the Bs being heads and tails, you get the exact same effect. So overall, when we judge how likely an event is to occur, and remember, this is a foundational part of the expected and subjective utility theory. We have to be able to judge how likely a certain event is to happen in order to calculate expected utility theory. So according to this heuristic, we don't quite calculate how likely something is to happen based on probability theory. Rather, we use this strategy that ends up making certain events feel more likely to occur than other events, even though from a purely probabilistic point of view, they're exactly equally probable.